Hello and welcome to Chemistry with Dr. Clark. In today's video, we're going to talk about writing the chemical name and the chemical formula for ionic compounds. Now, this topic has a lot of breadth to it. It's a lot of things you have to discuss. So for this first video, I've decided to limit myself to only the group A elements. So when I make my ionic compound, the only elements that I'm going to choose from are those from the group A parts of the periodic table. Now, this is the first part of the ionic naming video series. There are two more. The next video will talk about if you have group A and group B elements. And the third video will talk about if you have group A and group B and your polyatomics. So if you want to get a complete view of how to name and write chemical formulas for ionic compounds, there's actually a series of 3 videos that you'll need to take a look at. Okay, so let's start off by looking at what an ionic compound is. An ionic compound forms when cations, positively charged ions, and anions, negatively charged ions, attract each other. Now, the way it attracts is if you have a positive and if you have a negative, positives and negatives attract through electrostatic forces. All you have to do is put them close to each other and they will automatically attract. So for an ionic compound, all you need is some cations and some anions, and they will naturally gravitate towards each other to form an ionic compound. Now, one of the big questions with naming things, because there's also molecules and acids, there's various things to name, is how do I know that I have an ionic compound? The easiest way to know that you have an ionic compound is that it's going to have a metal and it's going to have a nonmetal. So if you look through my examples, sodium chloride, sodium's a metal, chloride's a nonmetal. Or calcium oxide, calcium is a metal, oxide's a nonmetal. Or aluminum sulfide, aluminum is a metal, sulfide is a nonmetal. Now, I do say usually composed of a metal and a nonmetal, because when you get to the third part of the ionic compounds video list, we do talk about polyatomic ions. A polyatomic ion can replace the metal or it can replace the nonmetal. So you could eventually end up with polyatomic plus nonmetal or metal plus polyatomic. Or in an extreme case, you could have polyatomic plus polyatomic. But we'll talk about the polyatomics in a separate video. For this particular one, an ionic compound will always be a metal plus a nonmetal. That's how you distinguish it. That's how when you're looking at a list of these things, you identify, hey, this is ionic, and so I have to use the Ionic rules. Now, the Ionic rules, there's not a whole lot there. First thing, when you write the name, the metal is always named first. So we'll name the metal first, and we don't change its name. Right? If you look at the periodic table, sodium is listed on the periodic table as sodium. Calcium is listed on the periodic table as calcium. Aluminum is listed on the periodic table as aluminum. The nonmetal is always named second, and its ending always is going to change. So on the periodic table, chlorine would end in INE, but because it's part of this ionic compound, it's now going to end in ide, so it's a chloride. On the periodic table, oxygen ends in gin, but when it's part of an ionic compound, it ends in ide, so now it's an oxide. If you were to go looking for sulfur, sulfur on the periodic table ends in UR, but here we've changed its ending to ide. So the minute that your nonmetal becomes part of an ionic compound, it does change its ending. Chlorine to chloride, oxygen to oxide, sulfur to sulfide. Okay? And that's the big things to remember. Name your metal first, your nonmetal second. The metal name doesn't change. The nonmetal name does change to end in ide. Now, before we get into a few examples, there is one issue we have to deal with. In order to write the chemical formulas for these, you have to know the charges on the ions. Now, this is one of those things that is considered a pretty basic skill. Okay, it's not basic as in it's easy to learn. Basic as in every other problem you're going to do, this is going to be the basis for it. Okay, it's going to be like underlying everything. So my suggestion is that once I write the charges in here on my periodic table, that if you're allowed to, you should write it in on your periodic table. Depends on what course you're taking and if you're allowed to mark on your periodic table. And in any case, memorize them. Okay? If someone asks you, what's the charge on a nitrogen? You have to be able to say, nitrogen is a -3 charge right away. You can't hesitate at all because it's going to be the first step in a much bigger problem that you're going to be doing. Okay? Now, I do have a video that talks about charges on ions based on their valence electrons and based on Bohr diagrams. So if you would like more information on why these have the charges that they do, you should check out that video. Okay? So let's talk about valence electrons. If you look here at group 1A, this would be the first column in your periodic table. It has hydrogen, lithium, sodium, potassium, rubidium. Because they're in group 1A, that means they have one valence electron. Now, there's a thing called the octet rule. Maybe we should make a little note. Octet rule. Pretty much everything on the periodic table would like to have 8 valence electrons in its outermost orbital or its outermost ring. It would like to have 8 valence electrons, hence octet rule. So if you're in group 1A, you have 1 valence electron. In order to get an octet, you need 7 more, right? You have 1, you're looking for 7 more. What's the chances that you're going to be able to find 7 more electrons? You're not, right? It's going to be impossible for you to find 7 electrons. So in this group here, because it has 1 valence electron, it's never going to get an octet by adding electrons. So what it does is takes its electron and throws it away. Okay, let's say we draw the Bohr diagram for lithium. Lithium is element 3, so it has 3 protons in my nucleus. You have 3 electrons, right? Because atoms are electrically neutral. So if you got 3 protons, you got 3 electrons. That would be 2 in the first ring, and it would be 1 in the second ring. Now, if I take this electron and I give it away, that means I don't even need to draw this outermost ring. This outermost ring disappears because my electron disappears. That leaves me with a completely filled inner ring. And completely filled rings, those are good things. Now, this inner filled ring here doesn't have an octet in it. It only has 2 electrons, which would be referred to as the duet rule. That innermost ring is happy with 2 electrons. The next ring would like to have 8. The next ring would like to have 8. Now, even though the duet rule here is part of it, we really do just refer to the octet rule. And we say, hey, if you've only got 1 electron, there's no chance that you're ever going to get 7 more, so throw it away. If I throw away this outer ring, you're down now to just the inner ring, which has 2 electrons, completely filled, energetically stable, it's good. So everything in this first column would like to lose 1 electron. Now, if you lose 1 electron, let's do the math for this one, right? I started with 3 protons. They're positive. I gave away this electron, so it's gone. That means I've only got 2 left, 2 electrons. So that's like saying positive 3 and negative 2, positive 1, right? If you give away 1 negatively charged electron, then you end up with a positive 1 charge. Everything in this column will have a plus 1 charge. If we look at column number 2, column 2A has 2 valence electrons. Now, you would really like to have 8. It's an octet. So what's your chances of getting 6 more electrons to make the octet? You've only got 2 and you're trying to make 8. You're not going to get them. So what you're going to do is you're going to take those 2 electrons and throw them away. Kind of like this threw away 1 electron. If you throw away 2 electrons, you're throwing away 2 negative charges, so you'd end up with a plus 2. If you look at group number 3, 3A, you've got 3 valence electrons. You would really like to have 8, but you need to get 5 more, and that's impossible, right? You're not going to get 5 more electrons. So what you're going to do is take this 3 and give them away. If you give away 3 electrons, you end up with a +3 charge. Now, we do skip the 4 group because the 4A group has 4 valence electrons. It's in a weird place, right? In order to get 8, it needs 4 more. Getting 4 more is pretty hard. In order to give away 4, that's also pretty hard, right? Think of this like giving away puppies. Okay, if you have 1 puppy to give away, you could probably find someone to take 1. If you had 2 puppies to give away, you could probably find people to give 2 puppies to. But if you've got 4 puppies, right, it becomes increasingly more difficult to find good homes for them and give them away. So for this group right here, this column, it's equally as hard to gain 4 as it is to give 4 away. So this column here doesn't really do ions. Okay, it doesn't like to make ions at all. So we're going to skip this one. Now, let's say we move on to this group here. Let's say we talk about nitrogen. And let's actually draw a diagram. Nitrogen is element number 7, so that's 7 protons. It's a neutral atom, so it has 7 electrons. We put 2 in the first ring, and that means I have 5 left over to put in the second ring. Okay. Now, in order for this to be energetically stable, in order for this to be happy, it would like to have a filled ring. It would like to have 8, hence octet rule. So in order to make that ring filled, if you've already got 5, I need 1, 2, 3 more. Now you've swung to the other side of the periodic table. Over here, you had a very limited number of valence electrons, and therefore it was easier to lose them. On this side, you are now in the opposite situation, right? I've got 5 valence electrons. That's like trying to give away 5 puppies, right? It's going to be very hard to give away 5 electrons. It becomes much easier to gain 3 electrons. So what's going to happen here is I'm going to add 3 electrons. Because if I add 3, this outermost ring becomes filled, it becomes totally stable. So if I gain 3 electrons, it's going to throw out my balance, right? In the original atom, I had 7 protons and 7 electrons. If I add 3 electrons, I've still got my 7 protons, but now I'm going to have 10 electrons. So a +7 and a -10. And if I add those up, +7, -10 gives me -3. So the charge on everything in this group is going to be a -3. Because they all have 5 valence electrons, they all need 3 more. And if you add 3 electrons, that comes with a -3 charge. Well, now you can see the pattern, right? If you're in group number 6, they all have 6 electrons. If you've got 6 electrons, that means you only need 2 more. And it's pretty easy to find an extra 2. So if you add an extra 2, this will become a -2. If you're in group 7, you've got 7 valence electrons. And if you've got 7 valence electrons, you only need 1 more. If you gain 1 electron, if you gain 1 negatively charged electron, this becomes a -1. Now, this last group over here is your noble gases, your inert gases. They already have 8 valence electrons because they're in group 8. Okay? So if I look at this periodic table, group 1 has a charge of 1. Group 2, when they become ions, will have a charge of 2. Group 3 will have a charge of 3. Group 5 will have a charge of -3, because you need 3 more electrons plus the 5 to make 8. Group 6 will have a charge of -2 when it becomes ions, because if you have 6 valence electrons, you need 2 more. And if you're in group number 7, you only need 1 more electron to give you an octet. So these ions will all be -1 charged. We skip column number 4 because they really don't make ions. And we skip column 8 because they also don't like to make ions. Now it does have a nice pattern to it. Plus, 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 minus, minus, minus. 1, 2, 3, 3, 2, 1. it makes memorizing it much, much easier. Okay, so like I said earlier, this is one of those things that's extremely important. And so you really should memorize which column has which charge. So I have a bit of a smaller periodic table here. Let me jot note them in. Group 1 has a charge of +1 when they become ions. Group 2 has a charge of +2 when they become ions. Group 3 has a charge of +3 when they become ions. This group doesn't do ions. And then it's -3, -2, -1. And this group doesn't do ions. Now, we should talk about the charge going down the group. On your periodic table, there's a staircase. Okay, so in most periodic tables, it's like a heavy black line or a heavy blue line or a heavy red line. And what it's meant to do is to separate metals from non-metals. Your metals are on this side. So when I make ionic compounds, my metals will come from here. And my non-metals are on this side. So these would be my non-metals. So when I make my ionic compound and I am looking for a non-metal, I'll look up here. So when I say that this column here is +3, really the only element that does +3 in this entire column is the aluminum. Okay, the boron, turns out, is a non-metal, and non-metals like to do negative charges. Boron's a bit of an exception. Okay, so boron doesn't usually do +3. Turns out your gallium and your indium also don't really follow the +3 rule. Okay, the only thing that really does a +3 in the +3 column is the aluminum. Okay, that's a little unfortunate because when we do these things, it's really neat to have something that has a +3 charge. And so if I want a +3 charge, my only option is aluminum. Now, if I look at the -3s, nitrogen will do a -3 ion, phosphorus will do a -3 ion, arsenic will do a -3 ion, but it really stops here. Okay, it doesn't include the antimony at the bottom. Same thing with the -2s. Oxygen, sulfur, selenium, and tellurium. All of these will do -2 as a charge. Now, I didn't write in the next row of my periodic table, but the next element here doesn't participate. Okay, so when we talk about these charges, column 1 is great. Everything in column 1 right to the bottom has a +1 charge when it's an ion. Okay, that is well behaved. Same thing with the group 2. But when you get over here to the other side, +3 is problematic, -3 cuts off before it hits the bottom of the column, and -2 cuts off before it gets to the bottom of the column. Okay, so these are all things that you should know and memorize. Now, the other thing that I'm going to suggest, you're probably pretty early in your chemistry career. You need to be able to find an element quickly. So if I said, please find magnesium, you shouldn't have to be hunting for it. You should say, oh, magnesium, it's right there. Okay, so what I would suggest is turn it into a bit of a scavenger hunt. Okay, if you've got a periodic table and you have a friend who has one, let them name an element at random and then see how fast you can find it. Then you name an element, see how fast they can find it. It will save you so much time later if you can find elements on your periodic table without having to hunt for them. All right, so let's move on to our examples. So in this list here, I would like to write the chemical formula for each of the following. Now, the way this is going to work, I've named the metal, I've named the non-metal, and they're both ions. The best thing to do is actually write the symbol for a lithium ion and write the symbol for a fluoride ion separately, and then we'll decide how we put them together. So if we pull out our periodic table, if you look up lithium, the symbol for lithium is Li. Okay, so Li. Lithium is in group number 1, so it has a +1 charge, so +1. Fluoride is a non-metal. Okay, the non-metals always come second, so it's going to be on this part of my periodic table. So my fluoride is right here, so that'll be an F. Now on the periodic table, it is listed as fluorine, but remember, its name changes when it becomes part of an ionic compound. Fluorine is in group number 7, and 7 has a charge of -1. because you've added one extra electron to the 7 you already had. Now, I do have a video that talks about forming ionic compounds based on Bohr diagrams. So if you want a bit more background information, you might want to take a look at that. But the idea that we're going to use in this one is that the total amount of positive and the total amount of negative have got to balance out. So if I've got a positive 1 and I've got a negative 1, these are a match made in heaven. They're perfect. +1, -1, you have exactly the right amount. So when I put them together, I only really need 1 lithium and I need 1 fluoride. Because the lithium has a +1 charge, the fluorine has a -1 charge. They're a perfect match. Now, the way that we usually think of it as the charge on the metal tells you how many of the nonmetals that you need. So since the charge on the lithium is 1, I would need 1 of the nonmetal. The charge on the nonmetal tells me the number of metals that I need. Okay, you basically take the 2 and switch them. So if I've got a -1 on the fluorine, that means I need 1 of the lithiums. Now, in the world of chemistry, we tend to be lazy people, okay? I guess the appropriate word to be is concise, right? We don't want to write anything that we don't have to. So when we write this here, the fact that I had Li written down kind of implies that there's some lithium there, that there's at least 1 of them. When I write down that there's an F, a fluoride, it kind of implies that there's 1 of them. So when the numbers turn out to be 1s, we don't write 1s. So I would rewrite this as just LiF, 1 lithium and 1 fluoride. In order to make this ionic compound, that's all you need. Now, this lithium still has a positive charge. This fluoride still has a negative charge, right? They still have charges, but the minute you put them together, the negative and positive cancel each other out, and that's why we don't write it. When we write them separately, we show their charges, but when we write them together, we don't. All right, so let's try a second one. Sodium iodide. So if I'm looking for sodium, sodium is right here. Its symbol is Na. It's also in group 1, so it has a charge of +1. Iodide is a nonmetal. If I look around here, I find that the iodide is here. Now, on my periodic table, it is called iodine, but remember, it name changes. And if you're in column number 7, your charge is a -1. Now, the 2 ways we can think about this is that, again, it's a perfect match. You've got a +1 and a -1, and because they're a perfect match, you only need 1 of each. Or you could think of it as let's switch the charges to give me the numbers, right? If you want to know how many sodiums, it's based on the charge of the iodine, so I need 1. If you want to know the number of iodines, it's based on the charge of the sodium. Charge on the sodium is a 1, so you got a 1, right? You just take the 2 numbers and switch them. Now, we don't write the 1s, so this would turn into an NaI, sodium iodide. All right, let's say we move it up a little bit and look at our next example. All right, next one I'd like you to do is calcium chloride. So if I take a look at this, calcium is right here. So the symbol for calcium is Ca. Calcium is in group number 2, so calcium has a charge of +2. Chloride is over here. Chloride is right there. It is in group number 7, so it has a charge of -1. Now you can see that this is not a perfect pair, right? Calcium is a +2, chloride is a -1. Now, if you want to think about trying to match the charges, the total amount of positive and the total amount of negative have got to match up. So if you've got 2 positives, then really you need 2 negatives, right? So if you've got 1 calcium with a +2 and the chloride only has a -1 charge, then really you need 2 of them, because 2 of them will give me a total of -2 as a charge. So plus 2 and minus 2. It means you need 1 calcium, and it means you need 2 chlorines. Okay, so you can think of it like that. Or you can simply do the switch the charges thing, right? The charge on a chloride is minus 1. Therefore, you only need 1 calcium. The charge on the calcium is 2 plus, so you need 2 chlorides, which is exactly what I just saw, right? In order to balance the charges, I saw that if calcium is a plus 2 and chloride is a minus 1, then I'd need 2 of them in order to give me a total of minus 2 on my charge. Okay, so if I rewrite this, because again, I don't want to write that 1, I'd say calcium, no subscript, which implies 1, chloride with a 2. All right, let's say we want to do aluminum oxide. So if I go looking for aluminum, aluminum is my only positive 3 ion. I love aluminum, right? It's a little bit different, and therefore it makes it a bit more interesting. Oxide, it's a nonmetal. If I look through all of my nonmetals, oxygen is here. In the periodic table, it's called oxygen, but when it becomes part of an ionic compound, it becomes an oxide. Because it is in group number 6, it has a charge of minus 2 when it becomes an ion. Now you can see that this is definitely not a perfect pair. The easiest way to do this one is to take my 2 charges and use those to predict how many of each. So when I talk about turning this into an ALO, because the charge on the oxygen is 2, that means I get 2 aluminums. Because the charge on aluminum is 3, that means I get 3 oxygens. So in order to put aluminum oxide together, you need 2 aluminum ions and 3 oxide ions. Now let's talk about why we need that. If I actually write it out, okay, you've got 2 aluminums. That's aluminum 3 plus and an aluminum 3 plus, right? When you put that little 2 there, you're telling me that you have 2 of them. When you put this little 3 here, you tell me you have 3 oxygens. So that's an O2 minus, and another O2 minus, and another O2 minus. What's your total amount of positive charge? 6 positives. What's your total amount of negative charges? 6 minus. You now have exactly the same amount as positive as you do negative. That's why you need 2 aluminums and 3 oxygens to make this work. Because in an ionic compound, the total amount of positive and negative have to balance. Okay, this is what we're really doing, but when we cross the numbers, that's a bit of a shortcut. It's to make our life a little bit quicker, because usually writing chemical formulas is a step 1 in a bigger problem. All right, let's move it up, see if we can move on to our next 2 examples. So if I want to talk about magnesium oxide, ooh, something new is going to happen here. If I look for magnesium, magnesium is here. It is in group 2, so it is a 2 plus. That's magnesium 2 plus. And you'll notice that none of the metal names have changed, right? This was magnesium in the periodic table. It's magnesium in my problem. Okay, oxide. Oxide is right here. Used to be an oxygen, so that's an O. And we know that if you're in group number 6, your charge is minus 2. Now, if I look at this based on charges, I've got 2 positives, I've got 2 minuses. That's a perfect match. They were made for each other, right? 2 positives, 2 minuses, perfect match. So all I really need is 1 magnesium and 1 oxygen, right? They match perfectly. But let's say that you really like this cross thing, right? You really like taking the charges and switching them. So let's say that we do that. Okay, here's my magnesium, here's my oxygen. If I take the charges and use them to determine how many, right? If you've got a charge of 2 minus on your oxygen, that means you got 2 magnesiums. If you've got a charge of 2 plus on your magnesium, that means you've got 2 oxygens. Now, this is science. This is chemistry. We cannot have more than one answer for the same problem. right? I just got an answer of MgO, 1 to 1. But I also got an answer of Mg2O2, 2 to 2. We can't have two different answers. So the rule that we have is the little numbers, the subscripts that tell you how many, always have to be in lowest terms. So if you think of math, if you have 2 to 2, that's same as saying 1 to 1. It reduces down. So Mg2O2 would reduce to Mg1O1, and we don't write the ones, so it does become this. All right, let's try another one that's same theme. Right, if I look up my aluminum is my favorite 3+ because it's my only 3+. So that's Al3+. If we're looking for phosphide, now it is the second element, therefore I know it's a nonmetal. If you go looking for it, because we haven't used it yet, here's phosphorus. Phosphorus becomes phosphide as an ion. So symbol for phosphorus is a P. It's in group number 5, so it has a charge of -3. And you can see that we're having the same thing happen in this problem that we had in the last one. These are a perfect pair. You've got a 3 positive and you got a 3 negative. If they are a perfect match, you really only need one of each. One aluminum, one phosphide. But if you do the switch thing, okay, we're going to take the two charges and we're going to switch them. So aluminum, phosphide. Because the charge on a phosphide is 3, that means you have 3 aluminums. Because the charge on aluminum is 3, that means you got 3 phosphides. And it's a math issue again. If you've got 3 to 3, that's the same as saying 1 to 1. So this would become Al1P1. And again, we don't write ones. So 1 aluminum, 1 phosphorus, phosphide, would become AlP. So when you're writing these things, the easiest way to think about them is to take the two charges and switch them, because that will tell you how many of each one you have. And the only thing that you have to watch out for is if you start getting numbers that are not lowest ratios, like 3 to 3 or 2 to 2. Or potentially, let's say that you had a 4 to 2. If you had a 4 to 2, that would reduce down to 2 to 1, right? They both divide by 2. So when you're writing these things out, make sure that you always go to the lowest ratio. All right, let's say that we'd like to go in the opposite direction. Turns out the opposite direction, way easier. Because you literally just have to name the first one, name the second one, and you're done. So if I look at this here, my first one is an LIBr. And this is why I say you really need to get familiar with your periodic table, because the faster you can find things, the faster these problems will go. So if I look up Li, Li is lithium. And we said the name of the first element doesn't change. So this would just be lithium. Excellent. The second element is Br. So if I look up Br, I find it here on the periodic table. It is a bromine, ends in INE. But we know that the second word has to change. So instead of a bromine, this one becomes a bromide. Okay, so the ending changes. Now, the other thing I should point out here is when you're writing the names of elements, the names of ions, the names of ionic compounds, there are no capital letters. The names have lowercase letters. That's why lithium starts with a lowercase l. That's why bromide starts with a lowercase b. Do not use capital letters when you're writing the names of elements or ions. All right, let's move on to the next one. Rb. That one's a little different. So if I go looking it up, Rb is rubidium. It is a metal, so its name does not change. So that's Rubidium. The other thing I should make note of, you have a periodic table. Okay, please make sure that you spell the elements correctly. Okay, it just shows that you are conscientious and that you're trying to do your best work. Right? When you write down the name of an element and you misspell it, even though you have your periodic table, it does give the impression that you don't care. Okay? It's like if you were writing an essay in English class and you decided that you weren't going to use any punctuations. So no periods, no question marks, right? People can still read it and understand what you're saying, but it does show a lack of care. Okay, so make sure no capital letters. Now the second element is an S. So if I look here, S stands for sulfur, and we do change the ending. So this will be a sulfide. Now, see how there's 2 rubidiums here and only 1 sulfur? We don't make any mention of that, right? I don't need to tell you that there's 2 rubidiums, because like on the last page, you could figure it out for yourself if you needed to. Okay, this part of chemistry assumes that you're pretty smart, right? So I don't need to tell you that there's 2 rubidiums, because if I gave you this name and asked you to write the formula, you would look up your rubidium. You'd see, hey, that's a +1 charge. You'd look up your sulfide. You'd see that it was a -2 charge. And chemistry assumes that you're a smart person and that you can switch these 2 to tell me how many, right? So if you switched them, you'd find out that you'd need 2 rubidiums, but you'd only need 1 sulfur, right? I don't need to, in its name, tell you how many, because based on the charge, you could figure out how many, right? If we look back to the last page, you'll notice that in none of these questions here did I ever tell you how many. Right? I never told you that there was 2 aluminums and 3 oxygens. You figured it out. For this one here, I never told you that there was 2 chlorides. Right? We figured it out. So when you're naming these things, you don't have to tell me that there's 2 rubidiums, because I can figure it out. All right, so we move on to the next one. SR. You look on the metal side. SR is strontium. Strontium. No name change. The N is from the non-metal side. N was nitrogen. It becomes nitride, enzinide. And even though there's a 3 and a 2, I don't have to tell you how many of each. Because if you needed to figure them out, you could, right? You're smart people. All right, so if we breeze through the last 3 examples, right, this really is just an exercise of can you find them on the periodic table and write them down? Okay, so your Ca, that's calcium. S was sulfur, but becomes sulfide. Okay. Ooh. This one here has something different as well. If I look at Na, Na is sodium. You're going to find that you're going to see a lot of sodiums. We love sodium. But that Se, ooh, Se is a little weird. If I go looking for it, it's selenium. So Selenium is its name. But then I have to remind myself, the second name always changes. So it's not selenium, it's seleninide. So this would be sodium selenide. Okay, a little bit of a weird name. It's not one that you'll come across a whole lot, but make sure you change your ending for your second one. All right, last one. Mg is magnesium. So magnesium. And the F was fluorine, but it becomes fluoride. F-L-U-O-R. Used to be an ene, but it's now an ide. And for none of these did I ever tell you how many, right? Didn't say how many fluorides. Didn't tell you that there was 2 sodiums. Didn't tell you it was 2 rubidiums. When you name an ionic compound, you just write its name, change the ending of the second one, and make sure you got no capital letters. All right, so this is the first part of naming ionic compounds. It only deals with group A elements. The group B elements are a little bit more tricky. So if you want to learn about how to name and write chemical formulas for ionic compounds that involve group B, that'll be part 2 in this series. Once again, thank you for joining me here at Chemistry with Dr. Clark.